Hello everyone. In today's session, we will be taking a look into chemical equilibrium. So you can consider this particular video session as a very quick revision for your NEET examinations. Let us consider that we have a reaction, that is a reactant A which is going to react with the reactant B in order to proceed forward to give us the product C and D. In any case, a reaction, if it proceeds only forward, such kind of reactions we consider them as irreversible reactions. So this is a generalized equation for an irreversible reaction. Suppose if we have a reaction that is containing a reactant A which is going to react with the reactant B, but it proceeds to forward to give rise to the products C and D, and in these cases the C and D further reacts among themselves to give you the reactant A and B. That is, in such kind of reactions, they have a capacity to go through both the directions, the forward as well as the backward directions. Now, in such reactions, the reactant can turn into products and the products can turn back into the reactants. Such kind of reactions, we consider them as reversible reactions. So in a reversible reaction, what is occurring over here is there is a reactant A which is reacting with a reactant B to give us the products C plus D, right? Now, as this reaction is going in a forward direction, this is considered as a forward reaction. Now here, the rate at which the reactant A reacts with the reactant B in order to proceed to give me the product C and D, this particular rate of reaction we call them as the rate of forward reactions. On the other hand, if we consider the first equation over here, right? So in this particular reaction, as I said, if it is a reversible reaction, it has a tendency where C and D can both react in order to give rise to A and B, right? Now, at this particular point, what is happening is the C and D is reacting to give back the A and B. In such a direction, we consider the reaction is going in a backward state. So we consider it as a backward reaction. Now here, the rate at which the backward reaction is occurring, we will just simply consider it as the rate of backward reaction. Now, usually what happens is that whenever a reaction at equilibrium, whenever there is a reaction that is at equilibrium, so in such cases, usually a forward reaction rate becomes equal to the rate of backward reactions. Now usually we use the abbreviations such as R refers for the rate, F refers for the forward, which is going to become equal to the rate of the backward reactions. So when does this particular thing is going to happen? Only once the reaction reaches the point of equilibrium. Okay, now quite simple, let's take an example over here. Let's say I have a nitrogen, right? Nitrogen is going to react with the hydrogen at certain conditions, of course under the presence of catalysts like iron and the promoters such as molybdenum. Now once this reaction occurs, it is going to give rise to ammonia, that is NH3. So in order to balance the things, let us have here as 2. So 2 into 3, that is 6. So let's have over here as 3. So this can be utilized as a simple example for a reversible reaction, right? Now, when we speak about a reversible reactions, there are certain condition what a student should know. Especially with respect to the NEET examinations, the graphs are very, very important. Now, the entire graphs, these graphs, we are going to classify under two sections. The first set of graph that one will look forward is the concentration versus time. So, we have three important graphs over here. So, let us mark it over here. In all the cases, the concentration on one of the axes. So, let's say these are the concentrations, right? And on the other axis, we will take it into consideration of the time. So, let's have the time over here. Now, the first type of graph, what is expected from the student to understand is a concentration versus time graph. As any reaction starts, let's say there is a reactant A which is going to react with reactant B in order to give rise to C plus D. Of course, C and D are going to react back in order to give us A and B. Now, the first two we will consider as a reactant, which we will abbreviate it as R, and the next two we will give it as a product, which we are going to give it as P. The first nature of a graph is that as the time goes by, the reactants goes on reacting. That means the reactant concentration goes on decreasing, right? So, as the reactant concentration goes on decreasing, this is what a student can observe. That is, the reactant concentration goes on decreasing with time. On the other hand, as the time progresses, as the reactants react, the products goes on increasing, and therefore one can observe such kind of nature of a graph. Now here, if you observe the points over here, that is this point over here, this point over here, and this particular point over here. So these are the points, as one can observe that after these points, the concentration of the reactant is going to go on becoming constant, while the concentration of the product also is becoming constant. So, after this point, the concentration becomes equal, right? Concentration becomes equalized. Fine. So, this point at which one can observe the same trend, this particular time, this is considered as the time of the equilibrium, that is TEQ. So, at this particular point, what is happening is the concentrations are becoming constant. This is the first nature of a graph to say that yes, the things are in equilibrium. The second nature of a graph. When we take a look into the second nature of a graph, one would observe that as the time goes by, the concentration of the reactant goes on decreasing, right? So, let's say a concentration of reactant is decreasing. But at the same time, the concentration of the product is increasing. So, let's give it like this. So, this is the product which is increasing. So, in such nature of a graph, one can observe that at one particular time, what is happening here is the concentration of both are becoming equal. This is very, very important condition. So, here is where the concentration is going to become equal, and of course it is constant. A very important nature of a graph to say that yes, the reaction is in equilibrium. On the other case, the third case of a graph is one would observe that with respect to time, the reactant concentration of course decreases and the product concentration of course increases. This is what is happening. Now, after a certain interval, now let's say after this particular point zone, we can observe that the concentrations are becoming constant, but they are not equal. So, this is the point number 3. Now, let's consider this is a point where we can give it as TEQ, right? So, at this particular point, what is happening over there is the concentrations are going to become constant, but they are not equal. They aren't equal anymore, right? So this is the first set of graph, which is the concentration versus time. Once we head on to the next type of graph, that is going to be the rate versus time graph. So let's have the rate on one of the axes. So let's have the rates over here, right, and the time on the other. Okay, so now let's say that we have a reaction, that is the A reacts with B in order to give rise to C plus D, right? Now what happens is that, please try to understand that in these cases, the rate, if the rate of a reaction becomes equal to the rate of backward reaction, the rate of forward reaction becomes equal to the rate of backward reaction, only then the reaction is going to be considered as in equilibrium, right? So let's say that if A and B are going to react, that particular rate is given as R, because it is going to give rise to C and D, we are going to consider it as an RF. On the other hand, C and D can react to give rise to A and B. The rate at which these particular things are going to react, we will give it as an RB, right? So now only one of these graphs are going to be considered as a graph which states that the reaction is in equilibrium. Please do note, as the time passes, the rate of reactant goes on decreasing. On the other hand, this is the nature what you will get. Now what does this say is that the top one gives us the rate of a forward reaction. That means as the time passes by, the rate of forward reaction goes on decreasing, and as the time passes by, the rate of backward reaction goes on increasing. But there will be a point after which both of them are constant and as well as they are equal. So that is, the rate of forward reaction will become equal to the rate of backward reaction, and also they are constant. Only in such cases we are going to consider that yes, the system, the reaction is in equilibrium. On the other hand, if we do observe, there are another two types of nature of a graph what one would observe. That is, as the time passes by, the rate of reaction goes on decreasing, and after that of course it is going to become equal. Okay, so let's say this is an RF. On the other hand, let's take into consideration of the backward reaction. This is how the rate of backward reaction would be observed. Now if you take any particular point over here, this is a point where one would say that yes, both of them are becoming constant. Yes, they are becoming constants, but they are becoming constant, but they are not equal to each other. That is, the rate of forward reaction is not becoming equal to the rate of backward reactions, right? So in such situations we will consider them as the reactions which are not in equilibrium. This is very, very important. So what is a note that we should have mentally over here is that though the rate will become a constant, that does not refer that the reaction is in equilibrium. Fine. So the third and the final type of a graph that one would observe is that as the time passes by, what is going to happen is the rate of forward reaction, of course it is going to decrease, and the rate of backward reaction, of course it is going to go on increasing, but they are not going to be constants, they are not going to be equal. So again, in such situations we will not consider the system to be in equilibrium. right? So only one system is in equilibrium, that is when we consider the rate versus time graph, and that is the graph number 1, right? So this is a very, very important graph that one should remember. So now let's proceed further. So the next concept that one should understand is the laws, the law of mass action. So first we'll understand what exactly is the law of mass action. We will take down the definition, then we will proceed with respect to the equations. So according to the law of mass action, it states that the rate of a reaction, is directly proportional to the product. Product here refers for the multiplications. So is directly proportional to the product of the active masses, Now when we speak about active masses refers for the concentration. Active masses of the reactants each raised to their respective stoichiometric ratios. Raised to their respective stoichiometric ratios, or else you can consider it as coefficients. So let's understand this by taking a simple generalized equation. Let's say there is a reactant A, that is A moles of reactant A is going to react with B moles of reactant B in order to give rise to C moles of reactant C plus D moles of reactant D. So for this particular equation, if I consider the law of mass action, it states as the rate of forward reaction is directly proportional to the products of the active masses of reactants. So for the forward reaction, the reactants are A and B. So let's say that is the reactant A, and let me say that is a reactant B. But it also says that each of these reactants are raised to their respective stoichiometric ratios or coefficients. So let's say that we have an A here and we have a B here, right? So similarly, for a backward reactions, I can give it as an RB, which is directly proportional to C moles of C and D moles of D, right? So that is the concentration of C raised to C, concentration of D raised to D. This is what we have. So by any chance, if we just open up, what we are going to have is that if I just open up the proportionality symbol, I will end up getting over here as the rate of forward reaction is equal to Kf. Now what does this Kf refers for? The rate constant for a forward reaction. Okay, that's a rate constant. So A raised to A, B raised to B. Similarly, RB is equal to KB C raised to C, and the D raised to the stoichiometric coefficient, that is D. This is what will happen. Now what we should know is, at equilibrium, we can say that Kc is going to become equal to Kf by Kb, right? So, and also we know that at equilibrium the rate of forward reaction becomes equal to the rate of backward reactions. So these are the two important note what we should know. So as we proceed forward, Kc is equal to Kf divided by Kb, right? Now if we just utilize the previous concept, that is Kf is going to become equal to, now Kf will become equal to Rf divided by A, concentration of active moles of A raised to A, into concentration of B raised to B, right? So if we just simply equate those both, we will end up getting over here concentration of C raised to C into the concentration of D raised to D. The whole thing will be divided by the concentration of A raised to A and the concentration of B raised to B, right? So this is the Kc. Now Kc over here is considered as the equilibrium constant. We will consider it as an equilibrium constant, right? So now very important note is that if I have a reaction, that is A moles of A reacts with B moles of B in order to proceed to give me C moles of C plus D moles of D. Okay. Now by any chance, let's say if I am going to take these reactants as a pure solid, if I take them as a pure solid, or if I take them as a pure liquids, please note that active masses, in such cases the active masses are going to become equal to unity. Okay, done. Now second point is that this is our point number 1 and the point number 2. By any chance, if the reactants, okay, and the products of a particular reaction are in gaseous states, if they are in the gaseous states, then we will utilize the terminology Kp. Okay, so Kp equals to partial pressure of C raised to the coefficient C into the partial pressure of the reactant D raised to D, the whole thing divided by the partial pressure of A raised to A multiplied by the partial pressure of B raised to B. This is how we are going to give the condition if the reactants and the products are in the gaseous states. Okay, so whether it is Kc or whether it is Kp, remember it is always equal to Kf divided by Kb, that is the rate constant for the forward reaction over the rate constant for the backward reaction. Now we'll speak about the units over here. So as we take down the units, now let's say for a reaction A moles of A plus B moles of B gives us C moles of C plus D moles of D, right? Now suppose if we are speaking about Kc, suppose if we are speaking about Kc, then we will give the Kc as Kc is equal to active concentration of C raised to C into active concentration, that is active masses of D raised to D, the whole thing divided by active mass of A raised to A into the active mass of B raised to B. Similarly, we can have it for the Kp. So when we speak about the Kp, what do we have over here is a Kp is equal to the partial pressure of C raised to the stoichiometric coefficient C into partial pressure of D raised to D, the whole thing divided by partial pressure of A raised to A into partial pressure of B raised to B. This is what we have, right? So when we speak about the unit, please do note it down as the unit for Kc is going to be equal to the moles per liter. You can designate it as this, or you can utilize as moles per liter. On the other hand, for Kp, the things will be slightly changed out. That is, Kp is equal to, because we are speaking with respect to the partial pressures, pressures are taken into consideration of the atmospheres. Okay, so atmosphere raised to the change in the number of moles. So delta Ng refers for the change in number of moles. So let's take it down. Delta Ng is equal to, that is, number of moles of reactants minus number of moles of products, right? So a similar type of condition also exists, which we call it as the reaction quotient. Now let me say that I have a reactant A which is going to react with reactant B to give rise to C moles of C plus D moles of D, right? Now for a minute, let us say that the reaction has just begun. That means the reaction has not reached equilibrium, right? Now in such case, by any chance, if I take into consideration of the active mass of C, which is raised to its stoichiometric ratio, that is C, multiplied by active mass of D raised to D, whole thing divided by active mass of A raised to A into the active mass of B raised to B, right? Only condition is that what we have said is C, D, A and B, we are not going to consider their concentrations at equilibrium, only this is a change. Okay, so yet the rest of the things are the same. It looks almost like a QC, okay, sorry, it looks almost like a KC, but it's not. Here we designate this condition as QC, where Q is called as the reaction quotient. Okay, so that is the Q is equal to Q, you can give it as Q or QC, that is equal to concentration of C raised to the stoichiometric ratio C multiplied by concentration of D raised to the stoichiometric ratio of D to the ratio of A raised to A and B raised to the stoichiometric ratio B, right? Now what exactly is the use? Here small three conditions will arise. By any chance, when you are checking the value of QC, please do note these are the important points. So by any chance, if we are taking a look at the QC, if the values of QC will become equal to KC, if this is a condition, okay, if the values do match, then in such conditions we will say that yes, the reactions are in equilibrium. So while calculating the value of QC, let's say the QC value is greater than KC, we will consider that the reaction proceeds in backward direction. When it reaches equilibrium, it is much more prone to go towards a backward direction. That is, C and D will react and it gives more amount of A and B. Okay, so it will try to remain in the A and B type of reactants. So we will consider it as the reactions tend to proceed backwards. On the other hand, let's say if the QC value is smaller than KC value, then exactly opposite condition will arise, that is the reaction. These particular conditions, these particular reactions will try to proceed in a forward direction, that is, it proceeds in a forward direction, right? I'll update the next things in the next video. Thank you. May God bless you all.